Thank you very much for the kind introduction. Yeah, so today I'm going to talk about photoluminescence, transient photoluminescence of late Halide perovskites, and what to do with it. So this person down here, it's possibly me or you, and it holds in his hand a sample where he did a new material or new treatment. And this person asks the question, can this be used for climate neutral energy supply? And the next question possibly is, which power conversion efficiency could that currently reach this material, and what are its limitations? And hopefully I can show you today that actually trPL has the answer to this. So it can be very simple, predictive, and basically measure all the relevant properties. However, before we come to this, we should clarify what are actually the relevant properties for photovoltaic applications. So I show you here a sketch of a solar cell with an electron contact, a hole contact, and the absorber material in the middle with the conduction valence band. So if you shine light on this, you photogenerate electrons and holes. And what a solar cell should do in the first place is give you a voltage. Yeah. So the voltage is given by the splitting of the quasi-Fermi-levels, and this can be calculated with this equation. And the properties which go in there is basically the carriers in the bands. Yeah. So some of them are already there in the dark. So this would be the doping concentration, which is important. And then there are photogenerated carriers, and their concentration depends on the lifetime. And there is the intrinsic carrier concentration. And with these three properties and the generation rate from the sun, you can basically calculate the VOC of your material. And then the material should also give you a current. To extract currents, it's important to have a long lifetime and a large mobility. So the mobility is adding to this. And mobility and diffusion coefficient, they are connected to each other. So you have one, you have also the other. And if you have these properties, then you can, for example, do drift diffusion simulation of your material and see what's the impact of the lifetime or the mobility on the efficiency of your material. And the nice thing is that all of these properties, they are actually accessible by trPL, which I'll show you today. So today I'll just show you one sample. It's from Martin Stolterford. It's this triple cation lead halide perovskites. It's on glass, so no back contact. It's encapsulated, so we didn't want to have trPL in this case. I will show you, you can learn a lot, but it's also complicated. Adding contact layers makes it even more complicated. So we didn't do this. And yeah, what we do with this is measure transient photoluminescence, trPL, or also time-resolved photoluminescence. Is basically the same. It's the same, it's just another name for it. And what you do there is you have a pulsed laser, you shoot your laser beam onto the sample, you photoexcite it. The photoluminescence comes out, you block the laser light with a filter, and then you go into, for example, a photodiode, and you can do a single time-correlated single photon counting, and you measure the photoluminescence decay. And so it's the photoluminescence amplitude over time, and it decays. And what's maybe a little bit special about my setup is that I actually, most trPL transients are shown like here with arbitrary units normalized to 1. So I calibrated my setup to absolute photon numbers. So I know the amplitude and photons per square centimeter in a second, what's coming out there. And this actually allows you not to only interpret the decay, but also the amplitude of your trPL. And also I'm using a rather wide excitation spot. So the nice thing about this is you don't have to care about lateral diffusion. You're much more sensitive because you collect much more light, and you're not sensitive to height alignment. Okay, now we come to the theory part. I hope I don't lose you, but it's just 2 slides. So what we do is we come in with this illumination pulse, excites the perovskite layer, and the transient photoluminescence comes out. And after we measured this, we want to model this. Yeah. And the equation to model this is actually relatively simple. So this is the emitted photon flux here, and it just depends on the external radiative coefficient, and then on the distribution of the electrons and the distribution of the holes inside your material. And so modeling trPL decays comes down to modeling the evolution of these electron and hole distributions, for example, by the continuity equation. So if we have a look at these distributions, for example, we can zoom in this perovskite layer here. You usually have carriers which are there already in the dark equilibrium, we call this the doping. And you have photogenerated carriers. Because the light's coming from the left side, you generate more at the surface. Initially, this decays exponentially into depth of the sample. And if you do the diffusion modeling with the continuity equation, it will diffuse into the depth of the sample and recombine. And so if you plug these distributions into this equation up there, you get basically the non-geminate PL. And this is an established approach and really nice. And however, it neglects something. It neglects that actually each of these photons which coming in here, it generates an electron in a hole at the same position. And then you can write up that quite differently. If you don't use the frame of the sample as the position here, but you use the position of the photogeneration as the center of your frame, you can have a look at this electron hole pair here. And initially, they are very close to the position where they are photogenerated, and over time, they will diffuse away. And you can plug also this distribution up in this equation here. And you will get, from that, the geminate PL. And the term geminate, so it's an astrological sign. These are twins there. And you use this term because actually this electron and hole is a twin. It was generated from the same photon. And if these electrons and holes, which were generated from the same photon, again recombine to emit a photon, this is geminate PL. And everything else is non-geminate PL. Usually people don't distinguish that much. However, I like to introduce two terms for this. So one is doping PL, where one of the carriers which are recombined was already there in the dark. So this is doped carrier. And the sibling PL, where both of the carriers were photogenerated, but not from the same photon. And I'm doing this because these three different PL types have very different behaviors, especially in the trPL. And maybe important because I think some of the in the audience are possibly coming from organics. Yeah, and organics here also have geminate PL, but their carriers are very much bound to excitons and they don't split. So here, these geminate carriers are actually free geminate carriers. So the electron holes split, but they are still very close to each other, but free, not bound as an exciton. And there are actually very few reports. I actually just found one. So if someone knows others, you can send me a notice, but I just found one report on this geminate PL in Lattice perovskites, actually. So you can then combine this both. So the overall PL is the sum of the non-geminate PL and the geminate PL. And you can write this distribution of the geminate carriers as a Gaussian. And the nice thing about this is that then you can solve the continuity equation actually analytically. And the only thing that controls the geminate PL is actually the distance between the electron and the hole. Yeah? So this geminate distance here. And over time, they will separate. They will move away from each other, and that will quench your geminate PL. And this distance here is controlled by the diffusion coefficient, and actually this diffusion coefficient is the sum of the electron and the hole diffusion coefficient. So this is controlled. You can control this, or this can be modeled very nicely, simply, analytically. And now we're coming to some experimental data. So what I did here is I have this excitation pulse. It hits the sample, and I increase the intensity of this excitation pulse. And then I can measure the trPL transients here. And as I increase the intensity of the excitation pulse, also the intensity of the trPL decays increases. And these decays can be very complex. So we start with something simple, and we just start with the maximum amplitude here. And we can plot this maximum amplitude of the trPL. versus the intensity of this illumination pulse. Or we can also transfer this then or convert this into a mean photogenerated carrier concentration. And we can take our equation from the PL, and we know the profile basically from the because when we excite, we have this exponential decay, and we can get an analytical expression out of this. And so what we have here is actually that you can distinguish these PL types from their dependence on the carrier concentration. So if you are quadratic, you have this sibling PL. And from this, if you have calibrated your setup to the absolute photon numbers, you directly get out the external radiative coefficient, which is done in a similar way by Singular before. However, what they didn't do is they just measured up here in this range. They didn't have to look into the linear regime. And from this linear regime here, where you are limited by, or where is given by this geminate PL, you get out the geminate distance. So at the time resolution of setup, which is in my case, roughly 100 picoseconds, the geminate pair, the carriers, the electrons and holes, are 108 nanometers apart of each other. And there can also be doping PL, but this is low to resolve here. So we just know that the doping concentration must be below 10 to the 14 per cubic centimeter. And you may ask, why do I know actually that this is the geminate PL and not the doping PL? Because they both have the linear dependence here. And actually, when I started this work, I wanted to measure doping concentrations. And however, I got tricked by this, and it just took me a while to figure out that it's actually not from the doping, but it's from the geminate carriers. So geminate carriers doesn't has only dependency, the linear dependence, but it also has a very fast initial decay. And you basically see this here in the transients. At the same time where this injection dependence becomes linear, there a very fast component shows up here. And this is basically the fingerprint of this geminate PL. I also indicate for the other parts of this transients, which of these PL types dominates there. Okay, so let's have a look at this geminate PL. So we take a transient measured at a very low photon flux to have a look at this geminate PL. And this photon flux is so low that we only have 1 photon per square micrometer per laser pulse. Yeah? So I show you here an SEM picture of the sample, and I superimpose with an illustration of this. So in this area here, you would just have 2 photons per pulse, which then generate electron-hole pairs here. And the probability to find them initially is very close to the position where the photon hits. Yeah. So the distance then between these 2 photons is the non-geminate distance. And if you zoom in on a geminate pair, yeah, then the distance between the electron and hole from the same geminate pair, this is the geminate distance. And what will happen over time, carriers will diffuse and spread out. Yeah. And that's what we see actually in the PL decay. So that's the measured PL decay. And the purple part here is coming from the geminate PL. And the decay of this part is actually this geminate diffusion, this carriers diffusing the hole and the electron diffusing away from each other. And the modeling again gives us this initial geminate distance of 100 nanometers. And the speed of this decay here gives us the diffusion coefficient. Additionally, there's sibling PL, but this is not enough to model the transient. So there's still some PL missing, and this is coming from the doping. Yeah, and from the doping PL, then you get the doping concentration, 3 times 10 to the 12 per cubic centimeter, and the decay here in the end is just from the charge carrier lifetime from the recombination. So by doing this model with relatively few parameters, it's just 3 parameters, the geminate distance we already had from the amplitudes, we can model this. And we get quite reasonable values out of this because we, for basically the same sample, we also made hole measurements in this work, and we measured the mobility there. And if we translate this diffusion coefficient to mobility, it's very close to it. So it's very consistent with Hall measurements. And also, if we compare this doping concentration to the doping concentration we measured with Hall, it's also very close to it. So it's a very nice contactless way to measure transport and doping concentration. Let's move this transient a little bit to the side, because I told you actually this quenching of the PL comes from the electron and hole which move away from each other. So we can translate this into the distance to the next carrier. Yeah. And so at this point here where the PL starts, the distance to the next carrier is this 108 nanometers. Yeah. And it increases over time by diffusion till to a certain point in time, not the geminate partners anymore, the next carrier, but the non-geminate carriers. So this is this part. And then I asked myself, okay, what is actually this initial geminate distance between the geminate carriers? And I had a little bit of look through literature, and I found a nice work of Zhang. And I converted their data to this distance to the geminate partner. And it fits actually very nicely to my data. And what they measure from transient absorption, they have at the femtosecond time scale, they measure the hot carrier transport. They measure how far the carriers transport or how far the carriers separate during the time they need to cool down, and this is by ballistic transport. And so I can identify actually this length, which the initial separation of the electron and hole by this hot transport length, which they have during the hot transport. And basically, this is then also very similar to the grain size. So it looks like the intragrain transport in this case is actually mostly by hot carriers. They spread throughout the whole grain by hot transport. Then they are trapped there for a very, very, very long time over very many orders of magnitude and time. And then only at roughly a nanosecond, they start to diffuse across the grains. And actually, then you can also put in the exciton radius here, and you see that the excitons basically split within the cooldown. And so what we have a look here is at non-excitonic geminate. What else can we do with transient photoluminescence? We can apply the generalized Planck's law. I think this is very common or often used for steady state photoluminescence, not that, or only a few times for trPL. But since I calibrated my setup to absolute photon numbers, I can then convert this the trPL into a chemical potential. And I have to say that this equation, the generalized Planck's law, is actually only derived for homogeneous distributed non-geminate carriers. So it's not always valid, but actually in my case, it's a pretty good approximation, which I can show you in a minute. And so that means actually if you have such a calibrated trPL setup, you actually measure the transient chemical potential or transient quasi-Fermi-level splitting or transient internal voltage. Basically, it's all the same. For example, this was already done by Krückemeyer, for example. And now we can start to analyze what actually these decays of the chemical potential are. And so the initial decay, we've already seen this from the PL. The initial is the diffusion of the carriers, diffusioning apart from each other, and the later decay is from the recombination. Yeah. And that makes sense because diffusion means you increase entropy, you decrease the free energy, you lose chemical potential, it decreases the mean quasi-Fermi-level splitting, and in the end this decreases then also the internal or then also the external voltage. Yeah. So this is a way, basically a time-resolved way to have a look at the losses in a solar cell. And I can model this then explicitly for a homogeneous distribution, that would be the quasi-Fermi-level splitting for the homogeneous distribution, just decays by recombination. You have a little contribution then from the surface excitation of the non-geminate carriers. And you have a very large contribution from the geminate correlation. And this is actually, I think, not much talked about in literature, that actually this the loss of the geminate correlation is actually a fundamental loss or fundamental energy loss in a solar cell. And here in this case, it's actually 100 millielectron volts. It's quite large. And another remarkable thing of this, if you think of this geminate correlation energy, if you want to call it that way, it lives pretty long. So this is 10 nanoseconds here where it decays. And for example, there's a lot of talking about hot carrier solar cells, but these hot carriers, they just live picoseconds. Yeah. So in this case, you could use this geminate energy for much longer time, yeah, or by orders of magnitude. And it cannot be really used in a solar cell, unfortunately. One has to think of other ways of energy conversion. One way it already works out is converting your energy back to photoluminescence, because we have seen actually this geminate correlation, it boosts the photoluminescence. Now, okay, this was basically the fancy part. Now it gets more, I think, more to an area which can be used also to study your samples if you on a daily basis. Let's have a look at the sibling PL here, and have a look what dominates there, the transients. So again, then we are back in the frame of the sample. So we have the surface excitation in the beginning. You have this hot transport, which already broadens a little bit the distribution. And that's actually what I also see here, that you need to broaden this distribution a little bit. Otherwise, it doesn't work out. So also already there, I see this hot transport length. And then over time, the carriers diffuse and the distribution gets flat. And if you take then this transient, and you can again model this from the homogeneous distribution, you can model this recombination part in the beginning, but this initial decay here in the beginning, this is from the diffusion of the carriers throughout the bulk of your sample. Actually, the nice thing is that also here you get a diffusion coefficient, which is very much the same as you get from this geminate separation. However, actually, diffusion affects these different PL types very differently. So I show you this here in the modeling. So for doping PL, actually, it's not affected at all by diffusion, assuming there's no reabsorption. Basically, this is, I don't model reabsorption here. Yeah, but the sibling PL, it basically decays relatively slowly, and the geminate PL decays much faster. And actually, the difference here between the sibling PL and the geminate PL is a factor of 3 in the exponent. And that's coming from the fact that actually in this non-geminate frame, the diffusion is only in one dimension, because you are laterally, you have homogeneous excitation, whereas the splitting of the geminate carriers, they split into all 3 dimensions. And that's why this decay here is much faster. Okay, now we're leaving the realm of the transport, which we measure, and we're going, okay, here we are. And now we are going to charge carrier recombination. Yeah, we're back at our transients here. And now what I did is I not only modeled one of these transients, but I put them all into one model and modeled all of them. Yeah, and this part here, basically at the later times, this is all controlled by the recombination. And from this, you can get the effective lifetime. And if you have a look at this effective lifetimes here, you can see that it's not just one lifetime, yeah, but it depends on the photogenerated carrier concentration. And actually, this power dependence, it's still puzzling me. So this is a little bit strange. Because this would correspond to a recombination order of 1.43 or something like this. And this is not really in the textbooks. So usually non-radiative recombination is 1, and radiative recombination is 2, and Auger radiation is 3. Yeah. So this is something in between. So the non-radiative recombination here seems to be strange. I don't know exactly what it is. But what I can do is I can, again, because I calibrated my setup to the absolute photon numbers, I get from the amplitude of the PL, I actually get the radiative lifetimes out. And I plotted them also in here. And you can see that actually this effective lifetime here is not limited by the radiative lifetime, which is also was discussed quite a lot in literature, if this is if it's the case or not. For my sample here, it's not. And you can see that this radiative lifetime actually behaves as it should. So this would be then a recombination order of 2 in this range where it behaves nicely. And in this range, like in the very beginning, actually due to the geminate carriers, the radiative lifetime is actually shorter. And as they split, the radiative lifetime at low injection levels becomes larger till it reaches a level which is fixed by the doping concentration. Okay, so what else can we do with this? So basically the ratio here of this radiative lifetime and of the effective lifetime, it gives you the PLQY. It's the photoluminescence quantum efficiency. And then you can compare this with the photoluminescence quantum efficiency you measure really in your device, or not in device, but on your sample. So you shine light, continuous light on your sample, you increase the light intensity from below 1 sun to above 1 sun, and you measure how much photons coming out of this and what's the quantum efficiency of these photons coming out. And what is shown here is that actually this dotted line is the model from this ratio, so that fits very well to each other. And this means so PLQY and trPL basically you can exchange one to the other, and they are both consistent with each other. And also this exponent here is consistent with each other. And the next thing you can do is you can take this and do a detailed balance analysis and convert this into an implied JV curve, basically. So if you want to go more into the theory details, you can find this here in my work. But basically, from this radiative lifetime, you get the radiative limit. With Shockley quasar limit, just a little bit more specific for the real absorption. And from the effective lifetime here, you get this non-radiative limit. And what you can do then is you can estimate the VOC of your sample. And then you can also have a look to which photogenerated carrier concentration does this actually correspond to. And this then tells you actually what is the relevant lifetime in your sample. So for a VOC, for example, in this sample, the relevant lifetime is 330 nanoseconds. And if you go to the maximum power point here, then the lifetime is a little larger. So it's 930 nanoseconds. So, and that's, I think it's a rather important message, because lifetime is not a fixed value. So it can be very, very many lifetimes. But if you then correlate this to the implied JV curves and certain operation conditions, then you can find out what is actually the relevant lifetime. And yeah, you can also estimate then the implied performance of your material. Okay, another thing which you sometimes have in literature is that you take the whole transients, and you calculate in differential lifetime, or differential decay time. Sorry, decay time. It's very important to distinguish between decay time and lifetime. Differential decay time. So basically, you just take the PL signal here, and you do the derivative of this, and you get the PL, the decay time out of this. And that's a time-dependent decay time. And then what especially the Kirchheit's group likes to do now is to plot this differential decay time versus the quasi-Fermi-level splitting. So they also calibrated their setup to absolute photon numbers, and then you can translate this photon numbers into quasi-Fermi-level splitting. Yeah, and basically you can translate the whole curves over here into decay time versus quasi-Fermi-level splitting. And then you end up with something like this, which looks a little crazy, a lot of dots. And so I want to tell you a little bit what it actually means, is that all this purple area here, these decay times are actually from the diffusion. Yeah, so there the distribution within the sample is still inhomogeneous, and the geminate carriers have not split yet, have not diffused away from each other really. And the limit here into which it goes, this is actually the recombination. Yeah. So if you have a look here, if you want to find out something about recombination and want to speak about charge carrier lifetimes from this plot, you should have a look at these times up here. And then you should have a look where the quasi-Fermi level splitting is actually at the maximum power point in the VOC. And then again, this would be your relevant lifetimes. Okay, and now to wrap this all up is actually this is all consistent. So you have a certain recombination order in your sample. So classically 1, 2, 3. We've seen this is 1.4 in this case. So 1 would be non-radiative usually, 2 radiative, 3 Auger. Then you have the charge carrier lifetimes here, which change with a certain exponent injection dependence. You have the photoluminescence decay, which this factor here in this exponent. You have the photoluminescence quantum yield, which then also increases with an exponent depending on the generation. And you have the implied JV curve, which also has in the JV curve here this exponent here, which is the radiative ideality factors. Basically, all of these exponents are connected to each other by these equations, and all of this you can take one and convert them into the other. And this is all consistent in the end with each other. The only thing you have to take care of in the conversion process, there is this, what I call the age, and the age depends on either if you're in the sibling PL regime or in the doping PL regime. Yeah? So it's either 2 or 1. You want to convert one to the other. And my conclusion on these PL types is that they are very different. Yeah, so they're dominating for different regimes. The sibling PL is especially strong for strong photogeneration and weak doping. Doping PL is obviously strong for strong doping, and the geminate PL is very strong at the early times, basically, and at low injection conditions. They scale differently with the excitation intensity. The decay is very different if you have diffusion and redistribution in your sample. Also, the decay time, actually conversion to the lifetime is different. So for sibling PL, actually the decay time of your PL is half of the lifetime, where in the other cases it's equals each other. And as I have shown you, each of them has unique properties which you can derive from. So geminate PL has this whole transport distance, the doping PL obviously the doping concentration, and the sibling PL also the diffusion coefficient and the external radiative coefficient. And also then from this you can derive a bunch of other properties which basically gives you everything you want to know about your solar cell material. I want to acknowledge a few people. So Thomas Unold, the leader of my group, Klaus Schwarzburg, who helped me over the last years a lot with trPL and is always at hand. Martin Stolterfurt, from which I have the samples, and Orestes, my PhD student, who did some UV-vis and lab material measurements for this work. Okay, and with that, I want to thank you, and I'm open for questions.